See?
Assalamu alaikum and good morning, ladies and gentlemen, boys and girls. Let me welcome you to the second day of actually two symposia, and both are felicitation for the 80th birthday of our dear teacher and Dr. Tarak. Session is co-chaired by a very dear friend and colleague, Dr. Sundar Farooq from the University of Birmingham. And let me promise you that this session is an excellent feast of wonderful chemistry. And I'm sure that you will really enjoy the lecture that you will see, followed by a very interesting lecture on vaccine. So a mix of chemistry and biology, and this is exactly what is happening in the world. The most exciting discoveries are actually happening at the interface of chemistry and biology. And the first speaker, which I'm going to introduce to you, is a very dear friend. We met about 10 years ago when he visited us from the University of Durham for one of the symposia which we organized, and since then we had this wonderful, cordial, positive, excellent, and productive relationship with Patrick. Patrick is an excellent organic chemist, and his intellect is what I really admire the most. Patrick is going to speak to us on his topic, which is identifying and validating new drug targets for leishmaniasis. We have worked together with Patrick, and the introduction of Patrick, briefly I can tell you that he undertook his undergraduate and postgraduate training from with Professor Jim Thomas at the University of Oxford. He was a postdoctoral fellow with Professor Gilbert Shaw, who visited us twice, and we had the pleasure of welcoming him. Professor Shaw is, he was one of the most prominent organic chemists who played an extremely important role in method development. He was from the University of Columbia. Patrick has worked with him. He joined as a faculty at Durham University, and he is a fellow of the Royal Society of Industry. Currently, his research interests include research methodology development for carbon activation. And then, of course, we work in the interface of chemistry as well. Patrick, over to you.
So thank you very much, Iqbal, for the kind invitation to join this symposium and those very kind words, and not mentioning the cricket more than once this morning. For those who know, Pakistan thumped England last night. Okay, so why are we really here? We're really here to acknowledge Professor Patel. You can read the script, since we've heard all the data. I thought the best thing to do was quote another former Cambridge academic, Isaac Newton. It's not quite the correct quote, but it should be, if we only go further, it's only by standing on the shoulders of giants. Professor Atta has certainly been a giant of chemistry and a giant of science in Pakistan. So we owe a lot of gratitude for that. So thank you, and this is dedicated to you. Okay, so I'm going to talk about leishmaniasis. I assume people in the audience know a bit about it, so the introduction is going to be relatively short. But what it is, it's a vector-borne, the sandfly parasitic disease that has a digenic life cycle, so an insect stage, and a mammalian stage. The mammalian stage is an infected one, and we see these manifesting themselves in multiple forms. Cutaneous form, which is probably the most common in Pakistan, I think. Mucocutaneous form, destructive, and the visceral form, which is the most fatal, not treated. So what we have to remember is we're going to do most of our work in the promastia, the insect form, because that's the one that's easiest to handle. Really what matters is these compounds actually work. So just a few quick statistics of justification. They're quite scary, really. It's increasing, it's endemic in 90 countries. There are more, that's an underestimation, 12 million infected, because it's partly reported in many cases. There are 2 million new cases a year. This is probably the biggest impact. There's 3.3 million disability-adjusted life years. That's effective working life lost for this disease. If we categorize cutaneous leishmaniasis, there's a mental stigma that's now been associated with it. It's reckoned to affect about 40 million people. So it's a disease that needs work on it. And the real problem is, you can't see the thing up here, but it says basically there are problems with all the drugs. These are the current drugs. Every single one of them has problems. They're toxic, resistant, relapse. For example, these two antimonials, widely used for cutaneous leishmaniasis, 28 daily course of injections into the lesion. So that's sore, so it's painful, so patient adherence is low. What we really need is new drug targets and validated leads. We're an academic group, and I think Christian Betts showed something similar yesterday. If we think about the cost and the time to generate a drug, it's huge and takes a long time. There's not many of us. So what we try and do is, can we de-risk projects by identifying new targets and identifying and validating new leads? And I'm going to show you 3 approaches where we've tried to do that, or trying to do that through this talk. How might you generate new leads? Well, in the simplest term, you can break them down into a target-based approach where you have a biochemical target, a protein, an enzyme, or something. You validate that as a target, you then run a screen against it, set a compound to some sort of biochemical assay, you get a compound, and then you have to prove that compound works in the way you think it does. Validate, chemically validate the target. The other way to do it, the forward chemical genetic approach, is a phenotypic approach of a disease model, and that's simply the promasticate parasite in many cases. We can run a screen compounds that affect that disease model, and we get a hit. And then we have to go and find the protein or target if we're going to do structural-based drug design or whatever else. We need to validate that target. I'm going to show you an example of each, and then something that falls a bit in the middle. So let me start on the phenotypic-based approach. And for this symptom, I think we should start with a plant natural product. So this is some work I did with our peer Rossi Bergman from the Federal University of Rio de Janeiro. And early on, she had explored this plant which you find in the Amazon, Piper Duncum. It's used by the native tribes there to treat cutaneous leishmaniasis. And they did some activity-based fractionation. They came up with this simple chalcone as a potential lead. And this is the activity against the pro-mastigote. This is the activity against the a-mastigote. And has a modest selectivity index. And with a Brazilian chemist, which is described in that paper at the bottom, Artera was able to advance that chemistry to make this compound. And this was having problems in its synthesis. We got involved. We made this one as an intermediate. It proved to be probably more active against the a-mastigote with a higher selectivity index. And when Artera took that into an in vivo model of infection, it reduced the size of the lesion in the reduce the parasite burden, not kill it. But the real question was, it was difficult to optimize, and we had no idea what the target was. So if you look at chalcones, they do everything. There's arguably promiscuous compounds. So I did some work to show that it wasn't any of these sort of common activities associated with chalcones, but there's certain features they saw when they treated with a series of compounds. So jump right to the chase. What we speculated, if you're a chemist, you look at that, you know this is an electrophilic carbon, delta plus, soft center. The soft nucleophile in biology is going to be a silos. We speculated this might be reacting or depleting the silos, what we call in the parasite. So the first thing to do was test that. We went away very simply, simple bit of chemistry, alkylated the enolate, which corresponds to compound next dihydrochalcone. And then when you test that, what you see is dihydrochalcone is almost inactive, whereas this compound retains activity. So that double bond is essential. So that gave us confidence that we can go and use the chalcone itself as a way to identify the drug target. This sort of, summarizes, this sort of cartoon summarizes both my understanding of parasites when I started, and also the strategy we tend to follow. We take the molecule and we modify it somewhere so we can put a bit of fishing line on it, somewhere we can fish the protein target out. We put this alkyne on it, we can then treat this modified compound, assuming it retains the same activity into the parasite. If we have that file, microreaction happens. We've now labeled our target protein with this alkyne, lyse the cell, complete protein there, and then we do a Huiskin type copper catalyzed like condition. The AGI leads to some sort of affinity agent here biotin, and we can then use tablet pull down that protein and identify it. It actually doesn't work very well if you just use biotin. If you've got lowly abundant proteins or rescue biotin, it just loses the background noise. So we make a slightly more elaborate molecule, pull down agent, and that's this molecule here with a fluorophore as well as biotin. So a bit of chemistry for the students in the back. So this is the iridium CH activation chemistry that we do with the other half of my group. We use iridium to activate this carbon hydrogen bond, oxidize the boron that we introduced there, and then simple alkylation and aldol reaction with this product here. And this retains anti-chromatogenic activity. The toxic compound gets to macrophage, so it's not good as a drug, but it still works. So we make this something that's working the same way. We did that and went through that workflow I showed you on the previous slide. Just the top bit out, labeling. What we saw here was a string of bands lit up where we put all the components into that reaction mixture. And I'm going to focus on this band here at 22 kilodalton and this band here at 35. What we haven't done is look at all the other bands, now going back to do that. Maybe I'll come back to that at the time at the end of the lecture. We take that 22 kilodalton band, how do we know it's associated with the drug action? What we do is I do a simple, what we call a competitive activity-based probe experiment. We pre-treat with the parent drug, then we add the probe, then we do all things before and we look. What we see when we do that, as we increase the concentration of the drug, the band at 22 kilodalton is depleted in a dose-dependent fashion. The band at 35 kilodalton is not effective. So we're now confident that band at 22 kilodalton is associated with the chalcone drugs that we've been using. Okay, we can then explain the methodology. We take that alkyne, we do the process, we extract it, we cut the band out of the gel, we do a non-gel protein digest, we get tryptopeptide, and by mass spec, we can identify a string of characters that correspond to those fragments we see. And the slightly one here is the enzyme cytosolic paradoxine peroxidase. So you then have to verify that's really the case. So we were fortunate that Angela Cruz at the University of Sao Paulo had the antibody to this compound, so we were able to run the Western blot. And there we are, you can see it there, and actually what you see up here is the dimer too. So that corresponds to that band, does correspond to it. Single proteins, then we do the DIG and the DIG Western blot. So we can now we're confident that's actually a single protein in that band. This enzyme is part of the process that maintains the thiol pool, or the antioxidant thiol pool in the parasite. There are two forms of it, the cytosolic and the mitochondrial version. This one is far less abundant. This is the most abundant, one of the most abundant proteins in the parasites, we suspect. That's why we're seeing that as such a bright band. We're going back now, looking and making these mitochondrial forms to verify what happens there. It exists as a dimer, or rather as a pentamer of dimers. protein study. Just to verify, a few more other experiments that we can do to show that this is really happening. We can make the recombinant protein, and there's the cytosolic pyridoxine peroxidase. We have the chalcone, we see a shift in the peak corresponding to the mass of one chalcone unit. But we can't see a complete labeling of this protein. I might come back to that later. We use the blue compound, we see no effect. If we do thermal shift experiments, we can see what happens to that protein as we add the drug. We start destabilizing the protein. So what we think is happening here is as the chalcone goes in, that decamer, the dimers are breaking up. Once they're broken up, they're no longer functional because the two active sites one comes from each dimer. Further evidence that it is an important drug target. We did the CRISPR-Cas knockouts of it. And here, when you two copies, and when you knock out both of them, what you see is that the promasticates grow so well, and they have a very rounded shape and much shorter flagella. And the EC50 goes up, and the drug becomes less effective. It's not a significant jump, and we suspect that's indicative of the fact that chalcones have multiple modes of action, and there are multiple targets. Very quickly at the end, we then went away and we showed this protein is present in the promastigote and the amastigote. So it could be used, this target is present and it is a viable drug target in that sense. And again, the dihydrochalcone is relatively inactive. And finally, for the chalcones in this story, what we've got some idea is the inhibition of GX-MPX leads to ROS accumulation. We look in the promastigotes, we have the chalcone, and we measure the amount of ROS we get per infected macrophage. For the same population of promastigotes goes up. This compound has almost no effect. We look at the macrophage ROS levels. We have an infected macrophage, ROS goes up in it. The non-infected macrophage, the chalcone has no effect. So that ROS is coming from the parasite. So what we think is happening is the chalcone is inhibiting the ability of the parasite to cope with the ROS burst you get from infecting the macrophage. Okay, so that was a quick whistle-stop trip down a phenotypic drug screen process. Let's have a look at a target-based type way of doing this. Here you need to have a biochemical target, a biochemical hypothesis to start. And our biochemical hypothesis comes from single lipid biosynthesis. And based on the fact that single lipid biosynthesis is highly conserved across all eukaryotic cells. The pathway is pretty much the same. The slight shuffling of some of the orders of some of the enzymes, but when you get to ceramide, there's a difference between mammals, where we use sphingomyelin synthase and phosphocholine to make sphingomyelin. That's the essential phospholipid you find in the stratum membrane of a human mammal cell. Whereas the parasites use this enzyme inositol ceramide synthesis of phosphoinositol to make IPC over here, and that's visible. The complex single lipid found in the stratum membrane of Leishmania. So the difference between the two of them, we wondered if we can inhibit that, we get a difference between host and parasite. And why do we think that might work? Well, if we look at this, the biochemical reaction, what happens is an active site histidine, which picks up ceramide from PI, gets phosphorylated enzyme, then that reactive ceramide forms IPC. And if we inhibit this process, we're going to see an accumulation of ceramide, and that's cytotoxic to cells. It's a trigger for programmed cell death for apoptosis or equivalent in a parasite. So that was our hypothesis when we set off. So it's a membrane-bound enzyme, so we're not going to get a structure in easily. So what we simply do is we express it in a yeast background. We can then do a crude extraction using microthermal preparation. That enables us to develop a very simple assay where we simply can measure the amount of product converted to the amount of starting material using this fluorescent lipid analog. Again, Christian referred to this yesterday. Our first screening process, we looked at compounds that really have been used already in other drug structures. Obviously, that would be a drug resistant. So we were fortunate that a small company we worked with gave us this little data set they had with 1,200 bioactive compounds. 57 of those inhibited the enzyme in that assay to about over 70%. We should be retested in the parasite then. One compound stood out as being most active, more active than one of the currently used drugs in that same assay. That's this compound here, fumarate. It's an over-the-counter antihistamine So it's now off, it's no longer sold, but it was a very simple early H1 impact. So what I'll show you now is how do we use that to validate the drug target chemistry. Firstly, we show that it's a range, it works against both cutaneous causing parasites, both old world and new world, and visceral leishmaniasis causing parasites, Donovani, and advanced old world and new world. And the activity is really quite good at getting the bone mass to go. Again, as I said before, it's got to work in the A mass to go. And so we work mostly, so I'm working in Brazil with this. Amazonensis is one of the course evading cutaneous leishmaniasis in Brazil. We work with Amazonensis. Here again, we see it retains that activity. Which may now then say macrophage mastigo, and for reasonable selectivity against the macrophage itself. Okay, so we've got a compound that works in both pro-mastigo and amastigo. Is it on target? Okay, so we did a bit of clever, or rather my collaborator Paul Denny has developed a mutant version of the parasite. It's not a very healthy one, but it's the sphingolipid mechanism is bypassed in this. It doesn't grow very well. And what that means, if you test against this, you should see a reduction in sensitivity, and that's exactly what we see. If we add back in this module of sphingolipid synthesis, plasmid, we receive that sensitivity comes back in. So it clearly indicates that the sphingolipid pathway is important in this process. Okay, so then, I'll jump the slide. Other ways of looking at it, we said earlier that if we inhibit the enzyme, we should see an increase in ceramide. So we did full metabolomic study with Mike Barrett at Glasgow University. If you look at the right-hand two panels here, in the absence of clemistine, we see relatively low level of ceramide. In the presence of clemistine, the ceramides go right to the roof. And that's indicative again of that blocking. And all the other pathways follow that process. We go to the other side of the equation. We look at PI and IPC. What happens here? If we inhibit the enzyme, what we see is the ratio of IPC to PI goes down, and we see more PI left over. Okay. Again, it's just that we're blocking that particular transformation. Another way of verifying on target is to try and generate resistance. So we did that by sequential increasing the concentration. After a few passages, we can get low levels of resistance, not very resistant, but it is resistant. You sequence all those mutants you get, they all have mutations in genes that can code for sphingolipid biosynthesis. That again is consistent with this process. Importantly, what you can see here is that what it should say up here is there is no cross resistance to any of the existing drugs. We think this is going to be ultimately a good adjuvant to some of those other drug treatments. With all that, we felt and showed it non-toxic, acting at the amastigo, does it actually work in a mouse model? And so we treated it, we're comparing it with one of the antimonials with cantine, it's given intralesionally. What we saw is cantine is not quite as good as giving cantine intralesionally. If we give it intraperitoneally, it's far better, it's really active, it reduces the burn, the almost complete clearance of the lesion, parasite burden is down there. Disappointingly, the oral dosage for an oral drug didn't seem to work. So there was good news and bad news in this. Chemistry works if you get it on board. If you get it into systemic circulation, it works better than putting it directly into the lesion where the parasites really are, which is surprising. But so what we think is that clemistine has polypharmacology, and that's known. If you take clemistine, you get sleepy. And so if you measure the mice, this is in Portuguese, I'm sorry, and you give clemistine, what you should see is that they stop moving. But you only see that when you give it IP, you give it orally, they don't. So the oral form is not getting in, it's not getting on board orally, that explains the oral dose. Polypharmacology, that's clear. Again, you can't see this across the bottom. These are all the different receptors. So this is the H1 receptor that clemistine was designed to target. Clemistine is the blue bar, sorry, green bar, the blue bars and analog were made at one point. That's very similar structure. These are all the other receptors, muscarinic, dopamine, serotonin receptors. Clemistine is not a clean drug, it has polypharmacology. So is that polypharmacology contributing to the activity? So what's known is that an infected macrophage having this P2X7 receptor on the surface, or receptors on the surface, when they're infected, they get an enhanced expression of that. And that if you have extracellular ATP, they activate the P2X7 receptor, and that increases the ROS production within the macrophage, which leads to an enhanced cell killing effect. The clemastine fumarate also stimulates the P2X7 receptor. So what we think happens is that the clemastine is stimulating and has an immune response. And this is what you can see there. Well, here's the wild type. If we add the ATP, you see an enhanced effect of clemastine. The clemastine stimulating that P2X7 receptor. If we knock out that P2X7 receptor, we see no effect. Clearly, again, supports the process that clemastine has multiple modes of action, one of which is to stimulate the immune system. And that would explain why IP inhibition is better than simple intensity. Okay, just very briefly, what we've done now is we're taking clemastine, so we've moved away from repurposing, a little bit of medchem, a simple nitrogen switch here, moving the stereochemistry around. We have a compound which is epitope, more selective but lower toxicity. And we look at that host receptor action, it's now, a lot of those other off-target effects are now gone. So we can work away from ACRS2 to see them there. They're easier to manipulate, much easier to make. Okay, and it retains activity. So again, here we get these lesions that change. Okay, so that's the clemastine story. One very short story where I'm going now. Well, another way we're doing it, somewhere in between those, how do you do it? I want to look at now kinase drug targets. And this is a map of the human kinome. The red dots show where there are orthologous leishmania kinases. So there are quite a number that are orthologous. But I want to know that the tyrosine kinase up here has no orthologous leishmania kinase. They don't exist in leishmania. So how can you probe kinases as drug targets? Well, if you look at the cancer world these days, an awful lot of new cancer drugs are covalent inhibitors. We've already seen that we use a covalent drug or a covalent compound, we can identify protein targets. So our hypothesis was that if we take some of these compounds, we can maybe identify kinases that are responsible for leishmania that are druggable because we get small molecules of parasites to it. So I'm going to show you some work we've done with ibrutinib. Now, ibrutinib targets tyrosine kinase, it's going to be highly selective for it. Okay, so we're going to use that. Tyrosine kinase don't exist in leishmania. Remember that. Is ibrutinib selective or not? Well, at the low concentrations you use it in the clinic, it's very selective. You take the concentration up, so this is a 100 nanomolar, we use it much less than that. This is at 10 micromolar, and these are the number of kinases it hits. So it's not really a very selective drug at a higher concentration. So, how do you turn it into a probe? That's very simple. It's got this free nitrogen here, we should be operating. And there's our tissue slide. We're not just happy with that. We want to simplify it. So that bit of chemistry you saw out here in ibrutinib helps to find the selectivity. It binds into the hinge region of the site of the kinase binding pocket. We make analogs, we take that out. These should be kinase agnostic, they should be more promiscuous. We can do them by some simple chemistry here, but I won't jump through. Let's go at the end. We can either put an acrylamide on there, that will target a cysteine, or we put a sulfonyl chloride on there, that will target a lysine. These residues not in the active site, they're in the gatekeeper region. So what happens? Okay, so let's start off with the ibrutinib probe. You can see differences now between old world, new world type species, different kinase profiles of different parasites, which shows one of the problems is that you get these drugs, kinase targets may not be present. Importantly, you can see that we go from procyclic chromatogogue to metacyclic chromatogogue to the amatogogue. Again, the kinase profile changes as you evolve through the things there. If we want to start looking for that, we can do that. We do that competition experiment I showed you before. Okay, so if we pre-incubate with ibrutinib and then our compound, what we can see is we can start seeing inhibition of certain bands on the gel. We do that competition experiment. These two particular bands up here. In this band here, we were able to cut the band out of it. Here's the band expansion. We can see it as it goes out. As we lower the concentration of protein, we see the band. We take that band out, we can sequence it, we get pyruvate kinase. You can get pyruvate kinase. This is purified pyruvate kinase, the same plan. We denature it, we need the active enzyme to get that activity. More importantly, we can do that competition experiment and use other small molecules to target it. So this is a model study. Chaconin is a known inhibitor of pyruvate kinase. This is the difference in fluorescence that we pre-treat chaconin. So we can now use this to screen other compounds by new inhibitors. That's something we're actually working on developing assays to do that. It's like to scale one compound at a time. Just very briefly, we've moved to more high-tech approaches. Here's the different probes, and again, you now see like cysteine-dependent things, slight difference on the binding pocket and the sulfonyl fluoride. You can't really examine everything by gels. It's indicative, it's like a TLC, doesn't really tell you what's happening. What we now do is quantitative mass spectrometry. The process is pretty much the same, but a protein purification state, rich in the biotin, clean up there, and then we isotope label. We tag all the proteins, and this will tag the lysine, then we'll get NH2, and this is mass label. The sequence is different, C13, N15 label, they're all isobaric tags, so we know which one it is when it comes to the mass spec. We do quantitative mass spec from proteomics. Okay, so this is a pioneering paper in this field. I'm still learning about it. At this point, I collaborated with a fantastic collaborator with Celeste and Durham, who helps us with this, in it. What we can see here now is we treat with ibrutinib. This is untreated, difference away from untreated. The red ones are kinases, the other ones are other things that outplay that particular probe in that protein. Again, evidence that ibrutinib is not studied concentrated. So again, we take the C7 bit out there, we see a difference. We now begin to understand what the selectivity is controlled by the alpha-ranking group there. If we go from here, which is the sulfonyl fluoride, again, we start with the picking process. We're now picking up the gate, residue and gatekeeper nitrogen rather than gatekeeper sulfur. And you can do direct comparisons. So here it is. Here's the effect of this thing here. This is the difference between these two here. These ones where it's significantly different. It's a much bigger jump when you go to 16. Just go out for shoot me. This is a map of the leishmania kinome generated by Jeremy Mottram at York. And the ones in red are the ones they couldn't knock out using CRISPR-Cas technology. They deemed genetically essential. What we've now been able to map with just a simple probes here for overlay, we've been able to label those essential kinases. So now we're looking for tools to chemically validate those genetic knockouts, and they'll give us potential drug leads. And these are ones where we've got non-essential ones, and we see if genetic essentiality will create chemical essentiality. Okay, so that's where we are. And this is a really exciting bit of work. We haven't published anything on yet. Really, I think where to go, we'll go back to the challenge. So, a very quick summary. I think natural products, yeah, they're a great place to start. The challenges with activity of molecular target optimization. Active-based chemical proteomic method is probably the way to do it. And TXNPX is potentially a new mode of action. Single lipid synthesis is an interesting mode of action. Don't be accumulate against good lead. And yeah, we're exploring this idea of person drug combinations. Kinase biochemical probes. Yeah, this is the first round. Keep studying. As you might guess, I don't do any of this work. I just get to come to the nice places and meet nice people. People who really do the work on this slide, I particularly need to acknowledge Paul Denny and Bartira. They're my academic collaborators who keep it straight and narrow and all things parasitological. People in blue are the ones who did the work. Andy Merritt from LifeArc has been a fantastic support of that company project with compounds. Ezekiel and Kalesh from the kinase work is supported, well supported by these people, particularly CSRF and the SD network. I've been privileged to work with this on. Just to reiterate, sharing things is a good idea, and this came out in Betteratta's talk. Coaches help PhDs are great. This is Rebecca from Durham. This is Douglas from Rio de Janeiro. They both have joint degrees, one from the University of Durham, one from the Federal University of Rio de Janeiro. They both got their PhDs in both places. It's a fantastic way of doing science. So I encourage people to develop these things here. That's a great way to do it. So yeah, that's the current group. The only failure I've got is I don't have a Pakistani student in my group yet. I'm trying to correct that as soon as I can. So I thank them. I thank you. Apologize on over a few minutes, but thanks very much.
Thank you very much, Pratik, for an absolutely fantastic presentation. I know that we've actually passed the time, but I still really would like to have one or two questions quickly, if we have one. Yes, Abdullah.
Yeah, thank you, sir. Sir, you have mentioned cell phone and its analogs were anti-less linear, and you have used CRISPR-Cas9 for the deletion of PTX and PX protein. But when there was a deletion of this protein, this cell phone become inactive. So, and you have mentioned that this is the target for this cell phone. So, what is the relation between?
So when we deleted the chaplain, we saw the ET50 go to the right, and the chaplain becomes less effective because the target is no longer there. You take the target away because it's doing it. We don't see a complete loss of activity. The chaplain, we think, has multiple modes of action. The chaplain has polypharmacology. It's still toxic for the drug, for the parasite in some ways, but we've just lost one of those modes of toxicity. So that's what you would expect when you do a simple knockdown.
And it has any relation with the reactive oxygen species, because in one side I have mentioned when there was a deletion of this protein,
Yeah,
the loss protection was.
It should be come down. It's not the only way that the parasite can cope with loss. There are other methods there. And I think that's one of the reasons why it doesn't give us
This is the target of cell phone.
notably, there is a mitochondrial form of the enzyme. And most of the damage we see when we look at in the parasite happens in the mitochondria. So maybe there's a mitochondrial form which is less abundant, also saturated in the mitochondria, so it may be hard to pull out for us. It's more responsible for affecting that down. Therefore, yeah, I think the chaplain is part of the action. Sorry, CTX NPX is part of the chaplain target profile, but it's not the whole story.
Thank you very much. Okay, you exhausted the entire quota of questions. So sorry. But thank you very much. And again, I invite you to kindly appreciate the wonderful presentation. And now for introducing another friend of ours, a very high quality chemist, Professor Alan Cleave, I would invite my co-chair, Dr. Subla.
Thank you, sir. I would like to invite Mr. Dr. Alan Cleave for the next presentation. First of all, I would like to introduce him. Subject areas are basically the understanding to understand the mechanism of biosynthesis of natural products. He was born in Tunisia, and he's a professor emeritus in the University of Namur, adjunct professor at HEJ, and main areas of research are organic and inorganic synthesis, bioorganic chemistry, knowledge management. He has 372 papers, including 12 patents, 20 books, and a lot of chapters in various books. He's a senior associate to the UNESCO UNISA Africa Chair in Nanosciences and Nanotechnology, the University of South Africa, Cape Town, since 2017. He's fellow of the Chemical Society of Pakistan since 2014. He's the executive director of the International Organization for Chemical Sciences and Development, founder and president of the Janssen Prize for Creativity in Organic Synthesis, president of the Birkenstock Conference, Switzerland, International Prize Verniers for Knowledge Broadcasting in 1999, president of the Société Royale de Chimie Belgique, prix de l'Académie des Sciences for the work on steroid biosynthesis, visiting professor since 1996. So that's actually a brief introduction because the time is running out. I would go on like for another 15 minutes. So thank you so much, Mr. Dr. Alan Cleave, to aid with that.
Thank you very much for your so kind introduction. Now I have to note I'm very pleased, of course, to be with you today, and it's a great honor to be here again. The story I will tell you is some exceptional one that I read, and I would like to share with you. It's not an error. 2010. This is the lecture I gave 11 years ago. And in fact, at the time, I gave you the facts, and I have been unable to understand what we had got from our experiment with an enzyme was very important. In fact, I retired. I never published this work, except that one of my colleagues, I'm in the lab every day, there in organic chemist from Belgium, but also having a laboratory with 60 people in Wuhan, in China, one of the 1,000 talent there, asked me to help him to create a new journal. So I helped him, and then I received a call to give the paper. So I returned back to square one and tried to work after 12 years to that project. It took me around 2 months to look at and to propose the solution to that aspect. And it is the first time I will present that, have been published, and I will show you what happened after the publication. I would like, of course, to dedicate this conference to my colleague and friend, Sarah Tauberman. Anosterol is an extremely important natural compound which led to cholesterol in mammals and to ergosterol in fungi and plants since 800 million years older. It is produced from vinegar, acetic acid for chemists, and you see that this red carbon comes to all these places of lactose. The intermediate is oxidosqualene, as proved by Corey and Van Tamelen, and the brief comment, Professor Van Tamelen was a student of Gilbert Thorpe and the boss of Barry Sharp. You see some of the red spots are larger than the other one, which means it's coming from that. And this differentiates the understanding of the process described by Woodward against the one proposed by Sir Robert Robinson, proved to be wrong. Only on these different aspects. That means the folding is different. Remarkable, one single asymmetric center provides 7 asymmetric center. This is provided in our body of mammal, at the liver place. The enzyme from human and from fungi has been described, but never used to explain the process. which take place in producing glynosterol from the epoxy. How people explain? This is also another surprise. The first paper was described, and this is the way, by the Zurich School and Stork at the same time, 1955. In fact, they proposed that oxidosqualene, the numbering are different because this is the numbering of squalene, this is the numbering of steroid. First, come from a polycyclization and then a rearrangement. The cyclization in the liver by oxidosqualene steroid cyclide go that way, it's proposed, and then produce this sort of cation and initiate the migration of hydrogen and methyl groups, and end by the removal of a proton, which has been proved if you have the red tritium, your water is tritiated. Stork at Harvard in a seminar, never published, and the team headed by Wichinska, Nobel Prize at the time, have described this process. Look, it was in German, and this has been translated in 2005 by a student, and the student is a young lady working in the Sharpless group. As you know, Sharpless was the Nobel Prize for its oxidation of allylic alcohol, oxidation of double bond, and then after that, describe the click chemistry that has been described. In fact, how that seems to work. This is described as a cascade reaction, but it is not really proof that it is that which produced this intermediate. It could have been that it is stepwise, and you see, you have here the tertiary carbocation, the seventh time tertiary carbocation are organic chemistry you have expected. And the last cyclization, the next cyclization, provides a secondary carbanium ion rather than the tertiary one. Good, and this produces this intermediate that I told you about. It could have been that it produces this one and rearrangement leaves that one. And the reason of that is expected that in the enzyme, this carbon is very close to that one. And this is the reason why, because of that proximity, this cyclization occurs that way. This is a work of Sharpless long ago, 1972, after he got his PhD from Alabama. He only used epoxysqualene, but reacted with the Lewis acid in benzene. And you see, you have the 6,6,5 rather than the 6,6,6,5, 1% yield only. And it was a different folding that we will see that. Now, if you look at the cartoon that I have, this is a folding described formally by Stork and Deschenmodder the reaction by activation, it produced this sort of supposed intermediate, and this is due to the 4D I have mentioned to you, and how they imagine that. Well, they had two rules to think about, which are the classical rule, the classical reaction in organic synthesis. The first one is an addition of AB anti-periplanar, one go from one side, the other go from the other side. You see, you have two possibilities. And if you have two possibilities, that means the double bond comes this way or the other way around. And of course, all that change from this to that. And so having this rule of anti-addition followed by the anti-periplanar 1-2 rearrangement, because I show you not in stereochemical aspect to explain to you rapidly, you arrive to the fact that the fold should be that way. So that you understand, then all go down and you have the rearrangement that takes place this way now. You see, from the elimination of the proton, the methyl group comes from the back, the methyl group from the top, that means the green one, and then hydrogen to the bottom, according to that. And produce lanosterol with 20R stereochemistry. If you look at more precise process, you see the chair both conformation that are the orbitals that will bring together by the two sides to produce the carbocation. This is the carbocation. And this is the direction. If you want to make the migration, chemists think that you have to have a rotation that this p orbital is parallel to that. In fact, never such cation have been isolated. It is postulated. So to do that, there are two ways to do it. 60-degree anti-clockwise, that is shown here. You get that one. You have two colors on the p orbital. You see on the top in the gray one. Migration now takes place, and you have lanosterol. But unfortunately, the stereochemistry is a wrong one, S. So that means it doesn't give the right product. Your theory is wrong. That's all. There is another way to solve the problem. Is to turn 120 degrees clockwise. This is a blue. Now, by doing that, the law is white, and then migration occurs. To produce, of course, the 20R lanosterol. Why is an enzyme such 120 degrees come from? Why? Go that, because usually you don't turn this very long chain, very long battery. It took 36 years that E.J. Corey, also Nobel Prize chemistry, to support that the hypothesis proposed by Ruchitska and was not the correct one. He suggests that instead of lying in alpha-oriented, beta-oriented side chain occur in the process. And of course, instead of 120 degree rotation clockwise, you have only 60-degree rotation to work, and that proposed improved by only synthesizing the compound epoxy-20, possessing an extra double bond, and this extra double bond allows a stabilization of the carbocation, trapping for the first time integrated in take X-ray crystallography and prove that all that stereochemistry was correct. And so the correct hypothesis came to be the one which was correct. Outside, we have been interested to understand what's the role of that, to see, to change the stereochemistry of the lab or that. And so we decided to, first of all, make smaller this group and to see if by changing this one, we will have still the 20R, and if the 5-membering, because now this can move on, will occur. We also decide to synthesize the S stereoisomer, the Z stereoisomer, and to see what was the stereochemistry, what will be the stereochemistry 20R as this one or S, or is still the 5-membering. We synthesize this compound. We got this one with a natural stereochemistry here, but an Fi instead of the long chain provide the 20R stereochemistry as a natural one, whereas the other one, having the reverse stereochemistry, produce the 20S stereochemistry. That means the reaction is, as we would expect, stereospecific, as usually matter do. The yield was poor, but you see, in both cases, we had also 5-membering compound that we isolated. We also synthesize this one. You see the yield is higher. And if you don't have this tricyclic compound. If by other, if you do the other stereoisomer, you have only 36% of S exclusively, 16% of this S, and a large amount of the tricyclic compound. Coming back to the part you have two methyl, you see you have cyclization and also some tricyclic compound. Now going to the last one, which is a reverse stoichiometry of epoxy study, we got not at all the lanosterol 5 compound, but exclusively the tricyclic compound, explaining how complicated was the interaction between the last double bond and the carbon. Having finished this result, we understood that we had some problems here because we were increasing the size here, but at the same time, we were decreasing that size. And we decided to slowly grow two groups. Instead of a methyl group, you have an ethyl group, you have two ethyl groups, you have two propyl groups, and so on. And this is the result. Of course, there is no stereochemistry of steric cyclized to tetracyclic compound. The one who has two propyl groups doesn't cyclize at all. This was the first time that no cyclization occurred, complete recovery, and it doesn't give other products. It doesn't enter the enzyme, probably due to this bigger bringing the cycle here, the rest of the reality. And the last, now is almost finished. The last project was to make the ethyl and propyl. What will happen, because we know that not working, this one is perfectly working. The problem is that you have two stereoisomers. We synthesize the one or one close to the natural product, that means the stereoisomer, and it produces the steroid like lanosterol analog possessing the R stereochemistry, 74% yield. Now, what will happen with that one? The reverse stereochemistry here. We got 31% of the compound with the S stereochemistry, as we would expect. But 30%, that means 30% of that is a reverse stereochemistry. How to explain that? And that was the problem I was stuck, no understanding how to explain. 44% yield. So 70/30. So if you return back to the proposal of Corey, this one with a natural stereochemistry for the 20R lanosterol by superflexion, migration, 60-degree rotation as it proposed. On the other case, the same process is supported by when you do the other stereoisomer, 70% of the product you get is explained by the Corey hypothesis and process. Now, if you take this one, the 30%, which was a problem, you see that if you want to express that it provides the are sterochemins. You should make that using the correct 120-degree turn, which was again against the probably because Corey changed the hypothesis of Asian mother because of this 120-degree requirement. Now in our process, we have to use 120. What we feel, the system now is playing the process of Asian mother. And if you use Asian mother, that means now you use alpha oriented than beta oriented, you get the correct stereochemistry with only a rotation of 60 degrees. But it is superficial. So for this, the correct process is not described. So the nature can make the two process. And finally, what the Asian mother and Stock thought was not very, very far from the reality. This is a paper. It was published in a new journal, Chemistry, in the Chinese journal. And surprisingly, I got, after the paper was signed, an email, a copy of the email of the referee of the paper who sent his agreement to the editor and to me. I didn't know that he would want to. And this is what Sharpless, the referee, said. And he decided to write a commentary will appear in the same journal. That is the beginning. And this is the second part. Okay, I will not comment why he said that. And we had to synthesize extremely pure epoxy with control of all the stereochemistry of all the CC double bond. We had to synthesize the compound chiral only one enantiomer here. We had to prepare all the lanosterol analog and to compare them with the product we had by co-injection after structural determination to prove all that. We have to go to the place to get the pig liver, to extract it. And the work on these two compounds with ethyl and propyl has been done by a single student, Sam, and the late Dr. Dumont was helping me. All the work for identifying the compound or checking has been done at the terrible fantastic research institute in chromatography because it costed too much for us to check the proper column and so on. And by Professor Sandra. And I would like to thank you very much for your
Matrix. Thank you for your very informative lecture, Mr. Honorary. I'm sorry the time was running out, so we have to shorten it a little bit. But if the audience, they have any questions? Thank you.
Thank you very much, Professor Alpi. Let me introduce the last speaker of the day, a guest from the East, from Indonesia, and very fortunate to have someone of her stature. She's the co-director of research innovation and community development at a very prominent university in Surabaya, University of Erlangga. Professor Dr. Nain Anwar Pushpaning Singh is a chemist by profession, and she has been working on a whole range of different chemical problems. She has worked on isolation and structural installation of natural products. She has also been involved in synthesis and then later moved into biotechnology, which is a very often a very advanced move from classical therapy to more of a vaccine development. And she has done it through COVID-19 period. And she's going to tell us about what she has done during that very turbulent time. Humanity and Indonesia was certainly one of the most advanced countries to moving through the synthesis of vaccines. So that is all that.
Thank you. Thank you very much, Professor Iqbal, for our opportunity, and also all the ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. So before I started my sharing presentation, I would like with our honor to congratulate Professor Abdul Rahman for his birthday, and hope Allah always blessing of him. So, okay, ladies and gentlemen, I would like to share what our do in our university for this challenging of COVID-19 vaccine development in Indonesia. So I would like to introduce Professor Iqbal and also all the ladies and gentlemen what our facility in our university. I would like to introduce Universitas Erlangga in the a short introduction of our facility. And also thank you, Professor Iqbal and Comsec, because Indonesia then also appointed as the Center of Excellence for Vaccine Development for the Organization of Islamic Cooperation. And for researcher now is already in Indonesia, Professor Iqbal, and they will be also visit us in the next October 3rd and look for our facility, how we designing the COVID-19 vaccine. So before I mentioning the what we are already done and the result for the challenging of COVID-19 vaccine in Indonesia. So let me share how the impact of vaccinating on selected disease that already happened in, of course, in global. So we can see here that the vaccination also is very important. I think all of us is agree, because we know that COVID-19 and then a shock for all of us in the global society and infected so many people during the 2 years of this happening suddenly among our environment. So if we look the history of the vaccination impact, we can see here like vaccine of diphtheria started in 1940. We can see after the vaccinated, then the cases and spread extremely down, and also the other I think infected bacteria or viruses also by using the vaccinated or can be neutralized by the vaccine itself. So we can see here polio started in 1956, and also the hemophilus influenza B type is 1992, and also the measles in 1968. You can see here they are becoming reducing the case after the vaccination. So running for this one, and then when we started in the beginning of 2020 in Indonesia on March, I think it is come from China in the first infected in the end of 2019. So Indonesia started in the beginning of March 2020. So I just put here on the very updating data from the WHO dashboard for the COVID-19. We can see here until September 22nd, 2022, there have been around 610 million people are confirmed for these cases, and also around 6.5 billion is already also dead, and until September 19, 2022, around 12 billion global society is already vaccinated by the vaccine of COVID-19. So how about Indonesia? So Indonesia already confirmed until also the same September 22nd, 2022, we have already confirmed cases around 6 million people of Indonesian infected by COVID-19. Even though now it's becoming reducing, but it's still also happening in our country. So why in our country we compulsory use this masker, even though inside or outside of house and also office, and around 157,000 people are there. And the vaccinated in Indonesia is already done for almost around 400 million people with the variable of the dose, first and the second dose, and only very minimum to have a booster on the third dose of the vaccine for COVID-19. So allow me to just introduce, I think all of you is already know related to the what is the SARS-CoV-2 or COVID-19. We know that the important thing to be a target of the vaccine is the structural protein, the protein who build the whole virion of the COVID-19. We can see some of the vaccine product are also designing by using the spike. I think majority they are using spike as the target of the antigen to be the vaccine. And part of our part of the product of the COVID-19 vaccine is also used part of the spike, like RBD, the subunit of the receptor binding domain from the spike protein. And I think I think none of them using the other. So they are very focusing on this because the spike is the protein who bind, attack, and bind the H2 receptor in human cell. So we can see here that this COVID-19 genome is the single strand of RNA and the plus. So it's mean that yeah, I think this virus is not so really dangerous, so serious compared to the HIV, something like that, because this is directly go to the ribosome of the host cell of human cell, and then there will be replicated and synthesized of their new protein to spread to other people. So you can see here that their genome sequence is around 30 kb or 30,000 base pair. So this is more easy to sequence by using the new generation sequencer. And at the first time Indonesian infected by this virus, I think it's very limited of the laboratory who have the NGS machine in Indonesia. And yeah, luckily our university has this machine because we are handling more infection disease substances and also like virus or bacteria. So why we can in the 1st of March when Indonesian infected, we already can sequence the whole genome of this virus and also found a very unique variant at that time. So we can see there for the 30 kb or 30,000 base pair of this genome virus. I think it is a little bit big size of the virus, and the protein itself of the spike is also the trimer protein. So they have trimer of the polypeptide surrounding of this kind of the spike, and this is a very important role for the COVID-19 to infect the host cell or human cell. So you can see here how this virus infected the human cell. You can see here that many of the scientists looking now for the very unique site of the furin or kind of the one of proteases cluster that has in the human cell. So this is like a friend or enemy. It depends on how the cell of human cell recognize the S1 at the S2 site, because at the first step of this virus attack and bind with the H2 in the human cell as the receptor. The subunit 1 or the first subunit will be bind to the H2, but then the binding between the link between S2 and S1 and S2 will be cleared by the kind of the protein in the human cell. So the furin or TNPRSS2, this is belong to the human cell that recognize the sequence of the cleavage site of the furin or protease to the binding between the S1 and this S2 site. And after they cleave, so they can infect infection of the genome of the COVID-19 into the host cell. So, while we also do our research to check by genotyping of the many kind of the variant that we have found in our society that infected with virus. So we can see here that what is the difference between the furin cleavage site knowing of this kind of the S1 and S2 of the spike. So we can see here why this is a novel of SARS-CoV-2 compared to the SARS-CoV, the previous SARS-CoV. You can see here that in this sequence of the genome, sequence of the spike gene of the COVID-19 in the SARS-CoV, previous SARS-CoV, this is missing. So no sequence in here, but in this one, this is the sequence of the amino acid is recognized by the furin. So the cleavage site is in here to cut the S1 and the S2 subunit. So then when we can see then what happened after the point mutation come in the aspartic acid to glycine in the number of the sequence of amino acid in 614. So this is, I think, starkly then COVID-19 becoming more higher to spread to the and also infected to our people, I think, in the global. So we call it this strain. I think is very famous with the European strain because it started in in Germany and becoming started in February, I think, and then becoming more and more. And then the first strain of Wuhan disappeared. So in Indonesia, surprisingly, this is published with even in Nature September 2020, when we are very surprising with this kind of mutation, that we know that the aspartate and glycine is very simple, I think, amino acid, and then they becoming the spike is more often. The simulation of this, you can see here there are 3 colors of the primer of the protein, spike protein. So they are becoming easily open the structure. And then when we can see here, the RBD is the point, the domain that the H2 is going to be bind with this area. So the whole of the spike, this is only the site that binding with the H2, because they are more open, then easily to bind, and then will be more tight into the H2 receptor. So then we try to check this kind of the new variant at the time. It's very many of our people die in Indonesia. It's very fast day per day. Not only day per day, I think hour to hour, minute to minute. So many ambulance come and go, and also our room is very near with the teaching hospital and infection hospital. I think every 5 or 10 minutes, ambulance come and go. We are very also afraid at that time, and we then check, because in our laboratory, infection disease laboratory, we can check for the whole genome sequence. So this is our result by using the genotyping. We then put the probe on the mutation of the D to the G, and we check for the whole the patient that collected the DNA or the genome in our laboratory to check whether in Surabaya, because at that time in our city is really dark, not dark, not only red, but dark red. Yeah, it's at that time in Surabaya is very seriously take impact of this. And so why we our laboratory then try to check what happened in our city at that time. So this is the weekly reported, and then after that, the blue one is from the first strain from Wuhan. It's disappear and no this strain after that. So we check for a year, collecting from the March 2020 until March 2021. But this one, I think you can look only maybe for months or 2 months. After that, we start from the March 2, yes, this one until the April. quickly we done to check our patient to test this kind of the COVID-19 infection of problem cases. So we can see here, and before that, the Wuhan is very high, but then step by step, this the G variant is the majority and dominant is slightly increasing, and after that, we all the infected patient is always the G variant of 6 or 14. So we don't have any Wuhan anymore, and that and this reported is also very important. So then after this, we have also then our government then built a consortium, national consortium. So then divided into several clusters. The first cluster is to do the vaccine development for COVID-19. The cluster is consists of 6 institutions, seven institutions. The two institutions is research and development institution, and the other 5 is from universities. So and the other, because we are in the beginning, we found this one on the beginning of March. So then our government also built a consortium, national consortium for genomic surveillance of COVID-19. So after that, our government then thinking that it is very serious to support the whole, because Indonesia is archipelago country and we have so many islands. So not simple, yeah. It's not easy to us to collect the sample from other islands to come to Java, because we have Sumatra, Kalimantan, very far each other. So then our government from Ministry of Health, they refer the instrument for like NGS and RT-PCR to the east of this island, and then build a national consortium for genomic surveillance. So then we can check whether the Delta or Alpha, Beta, Delta, any kind of the variant who then becoming highly spread to Indonesia. We can then making a map of distribution of this kind of variant in Indonesian country to the people. So I think this is the first information that then make our government thinking that this one is very important. So why genomic surveillance then now supporting by our government. So we have now many NGS in its island, the big island in Indonesia, and university becoming the center for analyzing the WGS of COVID-19. So last night I just looking for a new or updating data for the whole genome sequence in the global data of COVID-19. So we can see now in the global data of whole genome sequence now is around 30 million for the total, and comes submitted by so many universities in global area. And how about Indonesian data? So due to the supporting of the whole genome sequencer machine, then now at the beginning we are only 2 institutions that can submit it, Ekman and Universitas Erlangga, and only 16 whole genome sequence at the 2020 at March and April, yeah, started at Indonesian at the time. But now we can see that we can then deliver. Even though the problem in the global more than 13 million, yeah, you can mention. I already mentioned before in previous slide, but you know that the data I think is still limited, provided by whole our society. So from Indonesia we have 35,000, and from our university is 2,000. Sorry, Prof. Iqbal. Okay, this is what time I think that.
I think 1 minute.
Oh, I'm sorry. Sorry. Okay, I'm sorry, ladies and gentlemen. So this is the strain that we use for inactivated vaccine virus. We designed from our patient in Surabaya, and this is becoming the effective. The important thing how to designing the vaccine is we have three points important: is immunogenicity, efficacy, and also the safety. So the three points, this is very important for us to start producing our own COVID-19 vaccine. So I think I will skip this one. So when we look for the vaccine in the global area, you know that before the vaccine can produce after maybe 15 or 20 years research done by the researcher or also industry. But now I think it's more related to the very sophisticated and also the improve of the science and technology by bioinformatics and also the many kind of the by genotyping and gen technology. So the vaccine is more faster. So for COVID-19 vaccine, for example, we can produce after the product research done maybe 1.5 years, like we also do for like almost 2 years of this time, because they can overlap of the clinical trial in first phase, second phase, and third phase belong to the FDA agreement and also WHO. So in Indonesia, of course, we do also the same by our FDA, Indonesian FDA. We can also overlapping the second, first, and the third phase of the clinical trial. Even though we can skip the animal trial now in the global, but we not skip it this because it's very important. So we did also the preclinical trial. So we can see there's so many products now. I can skip this one from Pfizer, Moderna, AstraZeneca. They are started also in the beginning of 2020, and then you can see it's very fast to there. I think they're more higher technology that we use, and then they can approval at the end of the 2020 and in the beginning of 2021. And then how about Indonesia then after that? This is the first Indonesian vaccine produced by ourselves. Also Indonesian factory or in the pharmaceutical industry. So then how this industry, Biotis, producing, we are not built, but we adapt from other industry overseas, the facility, etc. But the seed vaccine we produced by ourselves. So we can see here how the country funding for this vaccine development research. I think Indonesia still far from this, but alhamdulillah, we can also produce, even though maybe not still in this area. We can see this is the very, very famous product we use, but then we, alhamdulillah, we can do that. And this is the 7 institution doing together in the National Consortium of vaccine, COVID-19 vaccine with many kind of the platform. But our university then I think go forward maybe faster. So then our government support to do until the clinical trial, and our partner Biotis Pharmaceutical also think that this is feasible and can do also for Indonesian society demand. So why then this vaccine merah putih production is especially to fulfill the Indonesian COVID-19 demand. Why? Because starting in this year, because if we look for the, for the Biotis, they will preparing all the laboratory in the GMP standard, international standard, preparing the upstream, downstream, and mass production. And we, in Universitas Erlangga, do for the preclinical and clinical trial. So this is the journey of our vaccine development. And then the preclinical, we use mice transgenic with the transgenic that they have human H2 inside of the mice. And then for the this is the product on the power 10 on the power of 6, and then the yield 10 on the power of 13. So I think it will be very cheap when we product for our society. So this is with macaca. We are also use in our university. We have animal BSL3, so we do this also test in our university. So we use several kind of the years of the macaca, from the young until the elderly and also the pregnant one. So why then our clinical trial already finished with the phase 1 first, second phase, and the third phase. The totally 4,500 volunteer or subject, and already have interim report. And then our government, FDA of Indonesia, asked us to have the additional clinical for booster. So this is also already finished, and the next we will waiting for the AUA, and also will be do for the vaccinated of the young and also the children, and hope also booster for the young adult. I think this is no need. So in Indonesia, we still need this amount of the vaccinated people, around 96, and this one for the booster for the young, and this one for the children. Yeah. Alhamdulillah, this vaccine also already got halal certificate for the MUI or Majelis Ulama Indonesia. This is the institution for giving the halal product in the whole the food or also drug.
Thank you very much.
Thank you very much. Yeah. Thank you.
Thank you. I'm sorry. Rahman, thank you very much. You represent the fourth largest country in the world, the second, the first, the largest Muslim country, and the country which has started producing vaccine in 1876. So thank you very much for your contribution, and thank you very much to all three speakers and to all of you. We have to quickly move to the UB hall and come back in the next 20 minutes, inshallah. We'll start our next session at 11.